So what I'll present is joint work with my advisor, Didier Rémy. Let's start with a little bit of motivation. So imagine that we are writing a program in a functional, statically typed programming language with algebraic data types, OCaml, for example, and that we wrote an evaluator for a very simple programming language, or complex, so we have a constant, addition, multiplication, and maybe some other things. We also wrote an evaluator because that's probably what we want to do. It's still very simple, but there can be a number of other cases. And we realized that we made a mistake when writing the type of expressions. For example, we have a lot of binary operators, 2, that's already a lot. And we want to factor them into a single constructor, for example, to implement transformations in a more simple way. So we can change our type. And now what happens to all the functions we have already written? Well, what we would do as programmers in a statically typed language is that we would copy the function or just add a new, change the type annotation. And then we will look at all the occurrences that are pointed by the type checker, and we will fix them one by one. So that works quite well. We already have, we are quite lucky to have types to help us do that. But that's still a manual process. It may be quite long. We could introduce errors while editing the file. For example, we could, I don't know, switch U and V. And the type checker might even miss some places where change is necessary. For example, if we exchange 2 fields with the same type, there's no way for the type checker to understand that we should have changed this part. So what can we do to improve this situation? The thing that we are not exploiting is that in our mental model of program modification, we know that there is a link between the old type and the new type. So what we want to do is to keep track of this link while doing the modification so that we don't miss any occurrence and we can exploit this information to do the transformation automatically. So we will use a restricted class of transformations called Ornaments, introduced by Conor McBride, and he introduced the coherence property that we will use for lifting functions. It gives a sort of specification of the function that we would want to produce. So there has been some quite a bit of work on Ornaments. There is work by McBride and Pierre Dagan, who continued working on this. I actually started working on Ornaments with Pierre. There are also some people at Oxford, I think, Cohen Gibbons, that did things on using Ornaments. In all these cases, this is encoded in Agda. So this is a cool language. You can do a nice encoding with powerful dependent types. It's great. But that doesn't work in ML. We don't have all the metaprogramming facilities given by dependent types. And so we need to be, we need to do things a bit differently. So what we do is that instead of encoding them, we define ornaments as a primitive concept. The correctness of a lifting is not an internal property anymore, so it was an equality in the type theory, and now it's something we know externally. We want to do program transformation, so what we'll do is that we will restrict the transformation to stick to the syntax. This is quite a reasonable assumption. We don't want to change the functions too much, and if we have this and the coherence property, we can automate the lifting quite a lot. And we prove the correctness of our transformation. Based on this process and this proof, so we built a prototype tool for lifting functions that works on a restricted subset of ML. I'll give an example. So let's start again with our example. We have 2 types, the old type, the new type. And instead of just replacing the definition and trusting the type checker, we will define an ornament that describes the relation between these two types. This is an ornament OX from X to X prime. So it transforms constants to constants prime. And if U is related to U prime V to V prime, then add of U and V is related to binomial prime at prime, U prime, V prime, etc. You can notice that we don't really want to use, we'll never use U there and U prime there, so we can just collapse them. So we just use U and V. This is a more compact notation for the same thing. So once we have defined this relation, we can use it to list functions, because now we have a specification. So we start with our code, and we write, we specify that we want eval prime to be a listing of eval, where the first argument has been transformed using the ornament OX, and the second argument is left as is, because it's integer, it's good. So what does this mean? This means that if U and U prime are related by our relation OX, we want the evaluation of eval U to be the same as the evaluation of U prime. And so our tool will generate exactly this code without any further effort. So it looks like what we would have written manually. So what's good about this is that we have a clear specification of the function we want, and we know that the function we return respects this specification. In this case, we are lucky. Our relation is 1-to-1, so the result is unique. And so we have a painless way to refactor a huge, potentially huge program for such transformations. We can do other things with ornaments. For example, this is quite new. We have, if we start with the type of lists, maybe in some parts of the program we only use lists with 3 elements, for example, to represent vectors in space. And maybe we are not really happy about this because we are missing an invariant in our types, and the representation is not efficient at all. So we have 3 const cells and then instead of just triple. So let's write the type of homogeneous triple, and we can define the transformation from list of 3 elements to triples. This should be triple, using an ornament. So the list of 3 elements is mapped to the triple, and all other cases are mapped to the empty pattern. So this is an incomplete ornament, and we have restricted the possible values. Now, if we start with some function operating on lists, we can ask for its lifting to triples. So what this will generate is this. So what happens is that the map function has been unfolded to follow the transformation we did on triples, to switch from lists to triples. So this is a bit obfuscated. We could automatically remove the noise and get this one. So this is the code. If we want the user to edit the code afterwards, this is the code we want to have. We can probably trust a compiler to compile the previous code to something equivalent to this, but that's not good enough for programming. So what's cool about this? We started from an invariant that was already present in the code, but that was not apparent, and by duplicating some code, we have made it obvious that the list we manipulate are 3 elements long. This also allows a better representation, so we can use this for optimization. We could also use this for optimizing general lists, for example, using special constructors for short lists. This would be something that we could express in the same way. Another class of example with ornaments, this is actually an important thing of ornaments, and I haven't talked about, I haven't introduced it before in the presentation, is that we can add data. For example, if we start with the type of natural numbers, it looks quite close to the type of lists. So the only difference is that we have renamed the fields and we have some new data there. And we can write an ornament that relates natural numbers to lists. So 0 is nil, and the successor of a tail is cons of something in the tail where the tail has been transformed using the ornament. There's nothing surprising about this. What's different is that the relation is not one-to-one anymore, so we have this pattern matches a lot of things. So what happens when we try to transform a function? So we start from addition, and if we ask for its lifting, we can imagine that it will give something that looks like append, because it's roughly the code of append. So we ask for the lifting, and we get this code. It looks like what we want to have, except that there's some missing parts there, because the ornament, the coherence property doesn't specify anything about this, because it doesn't talk about the part that we added to the ornament. So what we have to do about this is that we have to specify a patch. This is something user provided that will give the additional information. Here what we do is that we match an n, that's a variable in scope for this thing, and we get the head of the list and return it. You can notice that we are smart with the transformations on patch. So instead of just inserting the patch there, which would create an apparently incomplete pattern matching, give tons of warning and be quite inefficient, we can simplify it automatically to just put X there. So here is for the examples. Now the question is how to do this in a principled way. And for this, I would like to start by talking about something else. How does one write modular code in ML? The idea is if we want to write code that works on many data types, we can start by writing polymorphic code that abstracts over the details, and then we can provide an implementation. For example, we do this with functors typically. So we give type and value arguments. Good thing about this is that we can, if we want another implementation, we can just pass the new arguments. So we obtain a new code with different implementation details. And we get a theorem for free that says that as long as A and B, the arguments are appropriately related, FA and FB will behave the same up to the differences between A and B. So that's cool, and we can't do that because our base code is not abstract at all. So what we'll start by doing, because this looks like a good process that we would want to use, is that we will take our starting code and we will generalize it. So what we'll do is we will find the most general version in a way that is independent of the ornament of the instantiation we will do later. And now we can find an instantiation of this most generic version with identity arguments that give back the base code or something equivalent. And to generate the final code, we can just give the right arguments that will be inferred from the signatures given by the user and obtain the lifted version. So that's getting a bit abstract. I'll give an example. So this is the generic version that corresponds to the function add. What has changed? We have added 3 arguments. And instead of matching directly on M, we ask for it to be projected to something that looks like natural numbers. It's not exactly like natural numbers. And instead of constructing the successor, we use this injection function that will do some transformations. For example, we have a patch that will give the additional information. If we want to get the identity instantiation, that's simple. We just have a patch that translates z to z prime, that adds or removes z prime as necessary. And the patch is not used, so we can put anything we want. And the add function we obtain there is equivalent to the add function we had at the start. If we want to get append, we can invent new arguments that will describe the ornament between nat and list. And this is the patch that is given by the user. And so we get this function append. That's almost good, except that this is ugly code. We don't want to commit this into a repository. We don't want to continue working on this code. We don't even want to read it. So we have to do something more. We have to do some simplifications on the code that will give something that's nicer. So what we need to do is remove apply the new arguments and inline them and do this kind of thing. And so what we have is, instead that the base code is equivalent to the generic code applied to some arguments, the final code is equivalent to the generic code applied to some other arguments. Now, how do we find a relation between the base code and the generic code? We just need to prove that the arguments are related, and then the results are related. And if we give the right relation here that will correspond to the ornament, we will know that this is the relation, the covariance relation we want. One last thing that we are missing there is that it doesn't, you haven't seen it on the previous slides, but in fact this encoding is not typeable in ML. So we have to introduce some more richer language that has a form of dependent types, lightweight dependent types, that are used to type our encoding. And what we can do once we have done that is we can introduce some special applications and abstraction in this language that we will color in blue, and that will be that we can guarantee are reduced. So we have a result that says that if we have a well-typed term under some conditions, all blue things will be removed by some reduction, without having to do any reduction of ML code. The simplification here does some other things, so it uses the equalities that we can learn from pattern matching to inline things, and that's why the patch was transformed to X. And what you obtain is a principled way to get from some base code to a lifted version with a process that we can prove is correct. Now we can implement this. So we have a prototype that works on a small subset of OCaml and that precisely follows the process outlined here. It is available online with many more examples. There's something that I didn't talk about in this, is that there's a question of patches. We consider that it's something that orthogonal, so we don't finding patches is code inference, and it's not the kind of code inference we are interested in. Well, just one interesting note is that when this property-based code inference might be a quite robust way to specify patches, because we can just write something that relies on the external behavior of the function, and this one would be enough to generate the function we want. You should read our paper, so there is much more in it. We define the intermediate language with dependent types. We define conditions that guarantee that we can simplify this language back to ML. We precisely give the encoding of ornaments in this language. We define a logical relation on this language and an interpretation of ornaments in this relation. We give a formal description of the lifting, and we put all this together to prove that lifted terms are indeed related at the correct ornament. So we have something that we would like to do from this. So we would like to write a new implementation that supports most of OCaml and piggybacks on OCaml's type checker. This would allow us to run this large-scale program and so make it useful for actual programmers. We would need support for gedits because adding an invariant is something we can do with ornaments that we don't really treat here. There is a question of how to write robust patches, so we have to consider this more. And our formal results don't take effects into account. The implementation is correct with respect to effects, but that's not proved. But what we are happy about is that we have a principled way of transforming programs along ornaments. The process uses abstraction, then specialization. And we think that's something that could be generalized to other transformations. So we'll try to do something with this. Thank you.
Okay, questions, please?
Hi, Ryan Newton, Indiana University. First of all, great talk. It's wonderful to see ornaments moving towards practical usability in this way. A couple questions. First, about expressiveness. From the talk, I couldn't see what category of patches this works for. It looked like you wrote an arbitrary function for the patch. So for instance, could I convert a field that is a arbitrarily sized list to an array instead?
No. So the class of transformations we are considering there is transformations that can be described by some mutually recursive functions that do pattern matching and don't have too much memory, roughly. And we can't delete information also. That would be the ornamentation, which could work by the same process, but we haven't implemented.
Related to that, I was a little confused about the deployment model here. So I would never actually want to commit code with the lift keyword, right? This would be more of a command to my refactoring engine?
There are a few possible ways to do this. If you're doing refactoring, like going from X to X prime, you will probably want to throw away the old code and the lifting code and just keep the final code and commit it. If you are doing this for optimization, for example, to specialize some program to some functions to triples, you might want to keep the lifting instructions for the list library instead of committing a new version. So if you fix bug in the original, you get the bug fixed in your copy. So this depends on exactly what you want to do with them.
Thank you. That makes sense.
Okay. Any more questions? Okay. I've got one. Can you compose ornaments?
Oh, that's a good question.
Can you compose ornaments?
Yes. So yes, we can compose ornaments. There are two compositions that are interesting. You can serially compose ornaments. So you do one ornamentation of one type, and then reornament the target type. So we can already do that. We just have to give two lifting instructions. Maybe an interesting case is the pullback of two ornaments, where in one ornament you add some data, in other, for example, you add an invariant, and you want to get an ornament that gives you the best of both worlds, so new data, new invariants, and you can combine already existing liftings. You should be able to combine them without writing any additional thing, any additional code to work on this composed ornament. So that's probably the most interesting composition, I think, or at least that I can think of.
I mean, the first one you didn't really answer, because what I wanted to know is, if you have two ornaments, do you get one ornament which represents the composition?
Yes, you should have one ornament that represents the composition. Yeah.
Okay, good. Okay, thank you again.